This is the first video for section 6.1 in AP Calculus, which is on slope fields and Euler's method. So before we get into all that, I want to talk about an example that we would have had last semester back in chapter 4. Let's see if you recognize a problem like this. It says find the function y equals f of x, whose derivative is sine of x, and whose graph passes through the point 0, 2. So this is the derivative, and the original function goes through the point 0, 2. And so we're trying to figure out what this original function is. Well, we would have done it by thinking through, okay, what function has a derivative that's sine? And so that would have to be negative cosine of x. So that when we take its derivative, we get sine. But it could also have any constant added to it, correct? So basically, we just integrated sine of x dx and came up with that. So then we get into the whole particular solution part. And so if our function is f of x, or y, equals negative cosine of x plus c, the particular solution tells us to substitute in 2 for f of x, or for y, and to substitute in 0 for x. So then the cosine of 0 is 1, so this would be a negative 1 right here. And so c would have to equal 3. So our function, our particular solution, would be f of x equals negative cosine of x plus 3. Okay? Hopefully all of that rings a bell with you. That's something we would have done last semester. So then what if you had a problem that looked like this? dy dx equals sine of x. Initial condition, y of 0 equals 2. Find y of x when y of 0 is equal to 2. So this is done in terms of what are known as differential equations. It's basically where it gives you the derivative and you're working backwards. Basically like integrating like we've been doing now. So the differential equation is dy dx equals sine of x. And they call it a differential equation because basically this is a derivative, isn't it? They're saying the derivative is equal to sine of x. The solution to the initial value problem is that y of 0 is equal to 2. So you could either write it as y of 0 equals 2, or you could write it as a coordinate pair, 0, 2. And so then you would find the solution to the differential equation. So we would find the antiderivative, or the general solution to dy dx equals sine of x. So the integral of dy dx is just y, and the integral of sine of x is negative cosine of x. And then we would put a plus c to describe all possible functions for which this would be the differential equation, dy dx equals sine of x. So that's your general solution to the differential equation. So then you would find your particular solution, just like we did up above when we were reviewing. We would substitute in our coordinate pair, and so we would get c equals 3, and so our particular solution would be y equals negative cosine of x plus 3, just like in the review from chapter 4. And the whole reason I did that is because I want you to understand that what we're studying right now, differential equations, is no different than what we did back in chapter 4. Okay? So a differential equation is any equation that involves a derivative. The order of a differential equation is the order of the highest derivative involved in the equation. So, for example, here, this was dy dx. It was the first derivative, so this would be in order 1. If you write it as something like this equals, I don't know, x cubed, then this would be an order 2, because it's the second derivative that they're talking about there. But we don't get into that a whole lot. So an initial condition determines a particular solution by requiring that your solution curve, or your solution function, passes through that given point. If a curve is continuous, then your initial condition pins down your solution for the entire domain. If your curve is discontinuous, then it's only going to pin down the continuous pieces of the curve that pass through that given point. So the domain has to be specified in the final answer. So let's talk about what in the world all that means. Here, for example, we want to find the particular solution to this differential equation, dy dx equals 1 over x minus 1 over x squared, that passes through point P at 1, 2. So I would start by integrating both sides. The integral of dy dx is just y. And then here we're going to go piece by piece. So if you can remember, the function that has a derivative that's equal to 1 over x, that would be natural log of x. And this right here, that's like negative x to the negative 2. So if we work backwards from the power rule, the original function would need to have an exponent of negative 1. And remember, the original coefficient, we take the coefficient that we want to end up with, which is a negative 1, and divide it by our initial exponent. So that would mean that our initial function was positive x to the negative 1, or 1 over x. So going back to here, this would integrate to positive 1 over x, and then we would put a plus c. So that's the general solution to this differential equation. If we have a particular point, we would now substitute in 2 equals the natural log of 1 plus 1 over 1 plus c. Okay, so the natural log of 1 is 0. 1 over 1 is 1. So we end up with c equals 1. So our particular solution is y equals natural log of x plus 1 over x plus 1. Now, basically what they were saying with all of this stuff at the top about the continuous and the discontinuous is that when you integrate it, you need to be sure to include any domain restrictions. So, for example here, natural log can only be evaluated for positive x values. So that tells us that our domain would have to go be x is greater than 0, or it would have to go from 0 to infinity. This function has the domain restriction that x just cannot equal 0. So it could go from negative infinity to 0, or from 0 to infinity. And then 1, there is no domain restriction on 1. So we want the restriction that includes both of these, so that would be this one, because if we use negative infinity to 0, we would not be able to evaluate the natural log function. So all that means is, once you come up with your particular solution, if there's a domain restriction, just make sure to slap it onto the end there. Okay, so let's try this one right here. This one says to find the solution to the differential equation f prime of x equals e to the cosine of x, for which f of 2 is equal to 9. So this could also be written as dy dx equals e to the cosine of x. So then integrate both sides, and so this would integrate to y, and then I would get over here and I would start thinking, okay, well, e is its own derivative, but I have a function up here that's not just a plain old x. I can't really do backwards chain rule here with this. So if you get stuck, this is like such a cop-out, but if you get stuck and this is not a function that can be integrated algebraically, then your solution is just to write it as e to the cosine of t dt going from c, well, why don't we call it a, to x, and then you would stick a plus c on the end. That would be your general solution, okay, and it would just be that a is any real number, okay? But for our particular solution, we have an a value. This right here is our a value. So our particular solution would be y equals the integral from 2 to x of e to the cosine of t dt, and then your constant is going to be whatever that y coordinate is. That seems like such a cop-out because you don't really have to integrate and solve anything. You just basically turn it into a definite integral that goes from your x coordinate to x, change your x's to t's, and your constant is whatever your y coordinate is. Okay? Not a lot to that, you just have to kind of do it. But that's only for functions that cannot be integrated algebraically. So you cannot just write this for a solution to every single one of these problems and expect to get your credit. So don't even try it. Alright, so hopefully the whole solving for a particular solution for these differential equations is making sense to you. We'll practice some with it, and then you'll have another video to watch with some more information.